Hello guys, welcome back to my channel based on African motives, still working on A-level mathematics. So in our previous class we had worked on mathematical induction, guys. If you still remember the introduction of induction, mathematical induction, where we had to work with the multiples and divisibility there. So we shall have a continuation, guys, this time working on transformation type of questions, but that will be on matrices. So it's actually induction using matrices, because you know that matrices actually we use them in transformation. So now we just want to, because mostly you will see that this question will be under transformation. You'll be answering questions on transformation, then later on it will introduce something on in induction, or it can be a separate question. So let's just say we are working with induction using matrices. All right, so this is the statement that you're given, guys, that you shall start with. There are so many questions that we have, but let us start with this question that we are given there. We are given a transformation matrix M, which is given by the that is 2 minus 1, 1 and 0. They prove by induction that if n is an integer, which is a positive integer, then that is supposed to be true. All right, so remember, guys, all we had, guys, there, that is the introduction of the statement already. This is your statement that you're already given. So this is your PN, this is your the statement that you're already given in matrices. So guys, remember the stages. Okay, so this is going to be my statement, PM to the exponent of n, which is equivalent to n plus 1, n minus n, 1 minus n. So I'm just repeating the statement that I already have here. All right, so from this statement, the M is actually given as this matrix here. This is your M. So you can substitute the matrix in place of M. That's 2, 1, minus 1, 0, like this, to the exponent of n is the same as n plus 1 minus n. Sorry for that, and that is 1 minus n, like this. Okay, so this is what you're going to have. So what you're going to prove, guys, the stages of proving, they're just one and the same thing. Remember, when you are proving, you're going to introduce to say, you're going to start by saying when you're going to start with n, when n is equivalent to 1, that means p1 must be true. P1 must be what? Must be true. So can we see that this is going to be true if n is equal to 1? So if n is equal to 1, that means we are going to have 2 minus 1, 1, 0 here to the exponent of what? Of 1, which is equal to, in place of n, substitute 1. So this is 1 here, which is 1 plus 1, that is 2. And this is 1, so it's minus 1. This is 1, 1 minus 1, which is what? Which is 0 here. As we know, guys, any number to the exponent of 1 is 1. It's that number. I mean, 2 to the exponent of 1 is 2. If it is 3 to the exponent of 1, it remains as what? As 3. So even a bracket, like a matrix, a bracket, whatever that you have, when it is expressed to the exponent of 1, it remains as it is, which is 2, 1 minus 1, 0, like this, is equal to 2, 1 minus 1, 0, which is what? Which is true. As we can see, it's true because the left hand side and the right hand side, they are equal. So that is what you have for a matrix there. So now we move on to say when n is equivalent to k, that means that definitely pk must be what? Must be true, or is also, let's just say, is also true. Even whatever that you have, guys. Okay, that's what you're going to have there. So in place of k, that means here I'm going to substitute now in place of k. This must be a true simplification. Minus 1, 1, 0 here, that's what you have. In place of n, now it will be to the exponent of what? K. So just substitute k, guys, everywhere. You're going to substitute k. That's going to be k plus 1 minus k, and this is k here, and this is 1 minus k. So that's what you're going to have. Just substitute k. So this, we are saying that it must be true, or that's what we have. So now when we are to prove, this is the major part, because this is your statement which you said is true. All right, so let's go to the proof part now. Okay, when n is equal to k plus 1, it's now you who is to prove now. So I shall prove that. I shall prove that that is pk, in this case is your m. It was the m, yeah, that is shall be true. So it was okay. Let's just put it as pk. plus 1, but that was your m like from that part, but this is what is also true. Okay, here you just prove, guys, all these statements actually, I don't know the grammar there. Yeah, guys, you are the ones who are good in English. You can just write a good, something that is nicer for you, all right? But in terms of calculations, this is what is best for you. You're going to substitute k plus 1 now in place of what? In place of n. So remember this, it was your n, so it's just the same here, guys. So it's going to be 2 minus 1, 1, 0 like this, to the exponent of n, which is now k plus 1. So it's now k plus 1, which is equivalent to, let's take note of this bracket. Okay, let me refer it back here. This is your n, which you're saying is k plus 1. So this is going to be k plus 1 like this. That's what you're going to have, plus 1. Okay, this is minus n, which is minus k plus 1. So it's minus k plus 1. All right, this is n, which is k plus 1. So it's k plus 1. All right, 1 minus n, 1 minus n, so it's 1 minus n, which is k plus 1 like this. This is your n, which is k plus 1. So this is when you substitute k plus 1. So you can actually simplify further if you want, or you can just leave it like that. So now remember, you are the one who is to prove. So you're going to choose any side that you're going to take, either this side or this side. And as you can see here, we've got an exponent. So to prove from this side to this side where there's an exponent, it's going to be difficult for us. So always we take the complicated side so that it gives us the simpler side, and this is our most complicated side, this one. So we're going to take this side. So in this case, I'm going to choose to work with the left hand side so that I will prove that this is equal to what? To the right hand side. Okay, so 2 minus 1, 1, 0 here, to the exponent of k plus 1. We are saying if we are to simplify this, it must give us this matrix. How is that possible? How is it possible? That is the question now. All right, so this is what you're going to do, just like what we did. If you still remember from our first class on induction, I told about the separation of the exponent so that you can refer back to your pk there. So this is just like the normal thing, x to the exponent of a plus 1 plus b, which is actually x to the exponent of a times x to the exponent of b, which means you are adding the bases which are the same. So in this case, you are referring to the matrix part, like that, the whole matrix as it is. So this was 2 minus 1, 1, 0 like this, to the exponent of k, which was multiplied to 2 minus 1, 1, 0 like this, to the exponent of 1. That is where you added the exponents. But you know that to the exponent of 1, guys, it's just like that. 2 to the exponent of 1 is just like 2. So this is the stage, but I want to prove. So how am I going to prove? Okay, previously there is a statement that we had here previously. If you still remember, there's a statement that we have here, which is for this bracket that is equivalent to this. So which means this matrix we can actually substitute. Okay, guys, let me put it this way so that it can be clear. Okay, let me just, okay, we had this matrix here, this matrix, which we are saying this matrix and this matrix, they are the same. So it means I can now substitute this in place. I can now substitute this matrix here in place of what? 3 to the exponent of k. From which statement? From where I am proving here. So this is what I'm going to do. In place of this bracket, which is this, the whole matrix, this one, the one that I'm representing as the bracket, the whole matrix, I'm going to substitute with its equivalent in terms of what? K. We say this is equal to what? To k plus 1. All right, here we say this is equivalent to k. It was the same as this one, okay, which was k plus 1 minus k like this. K, you just write everything as it is from your statement of what? From your pk there, you just write that statement as it is, guys. Okay, just write everything as it is. So if this is your statement, but remember, where are you going to apply this? You are going to multiply it to the one that you are having here, which is 2 minus 1, 1, 0 like this. So if I am to multiply and simplify, am I going to obtain this part on the right hand side? If I am able to obtain this part on the right hand side, then I'm done. Then I'm done. That is the case. So let's prove. Let's multiply, guys. You are back to your O-level mathematics row by column. That is, in this case, we've got this row by this is the actual row up to here by this column here. So you're going to multiply, guys. Let's multiply properly. So it's 2 times k, which is 2k plus 2, okay, minus 1 times k, which is minus k. We are done with this row and this column. You move on to this row, but with this column now. So it's minus 1 times k, which is minus k, minus 1 times 1, which is minus 1. Okay, we are done with this number and this number, and then we move on to 0 and what? K. That's minus k times 0 here, which is a 0. So it's just like plus 0, which means there's no effect there. All right. Anyways, let's just put it so that we all understand. Then you are on this row now versus this same first column that you had before. So it's now k times 2, which is what? Which is 2k in this case. Okay, take note, k times 2, which is 2k. Then 1 minus k times 1, as you can see, you're multiplying by 1. It just remains as it is, which is plus 1 minus k as it is. You are done with this part. Now is this same row, but with this column now, this last column. So let's do it, guys. That's k times minus 1, which is minus k. Then this multiplied by a 0, as you can see, just by multiplying by a 0, that's a 0 there. So which means we are just going to remain with this part. Okay, so the question is, guys, remember where the part that we have to prove. We have to prove this. This is what you want to prove. So you must write your answer like this, or if it is like it is simplified, maybe it can be like this. You expand the brackets. That's gonna be k plus what? K plus 2, and this one will be minus k minus 1 like this, and this one will remain as k plus 1. This one, if you expand brackets, it will be like 1. It will be like this, guys. It will be like this. I want you to see 1 minus k minus times 1, which is minus 1. 1 minus 1 is what? That's a 0. So it's minus k like this. So it means this part that we have to prove in its simplified version, that is the simplified version, which means is this part and this part, they are simply the same. All right, so let's see if we are going to obtain any of those two. So that's it, guys. Let's see. Let's equate here 2k minus k. That's gonna give us k. So it's k plus 2. All right, minus k minus 1 plus 0, which is minus k minus 1. 2k minus k, which is k plus 1 in this case, because it's 2k minus k here, and minus k plus 0, that's minus k, because there's nothing that you're adding here. So if you have to cross check this bracket here, this matrix that you have and this matrix that you have are the same, which means it's the same as this one. Actually, what happened here on this 2 was just written as what? 1 plus 1. This was it, 1 plus 1. So it means it's just one and the same thing, k plus 1 plus 1. This minus k, what happened here? In order to write like this, we just factor the minus. So if you factor out a minus here, you're going to have k plus 1. Here it's already k plus 1. There's nothing that you're going to do. Minus k, we said minus k is same as 1 minus what? Minus k plus 1 is simply one and the same thing. So this is what you're going to do, which is actually equal to what? To the right hand side, which is true. So we managed to prove that this is true. So after proving that this is true, therefore you can actually conclude now. Remember, your conclusion is just the same. You choose a conclusion of your choice. So that's why I don't write my conclusions, because you might think that this is the best conclusion, of which no, it's not the best conclusion. Your conclusion is the best conclusion. So write your conclusion, the one that you are best at, and make sure that you stick to that conclusion so that you can be able to attempt as many questions. Like don't try to mix up conclusions. Today you are using this conclusion, tomorrow you are using this conclusion. No, just stick to one conclusion. Okay, so I'm having another question also, that is from one of the question papers again, which is matrices. We are given the matrix A that is given by the matrix that is 2A and so forth, and we are given the statement. So this is the statement, and we are working with the positive integers to prove by induction that this is true. All right, so just like the previous part, guys, I'm just going to take this as it is. That is my a to the exponent of n, substitute here with a, which is this part here. Since we are given that a to the exponent of n is equivalent to 2 to the exponent of n, 0 here. I'm rewriting this statement here, so I'm going to explain from this statement, which is 2 to the exponent of n minus 1 times a, that is a 1, like this. All right, so from this statement, let me say my a, because I'm given my matrix A here. So this is your matrix A, the one that you're going to substitute here, which is 2A 0 1. Okay, so let's just substitute there in terms of A. That's 2A 0 1, like this, to the exponent of what? N, which is equivalent to 2 to the exponent of n. So this one, we are given that these two, they are equal. They are equal. All right, so if these two are equal, it means we have to try and see if truly they are. So when n is equal to 1, then it means our statement must be true. So n is equal to 1. So proof when n is equal to 1, guys. Okay, so let's substitute when n is equal to 1. As you can see, this will just remain as a 2a 0 1 in this case, which is equal to the exponent of 1. That's 2 to the exponent of 1, which is 2, 0 here. This one is going to be 2 to the exponent of 1 minus 1 times a, and you're going to obtain 1 times a, which is a. So this is a, and this is just a 1. So as you can see, these two matrices, they are equal, which is true. Okay, and this is actually true. All right, then we move on now to say when n is equal to k. When n is equivalent to what? To k, this must be true also. So this is just true. It must be true if it is equal to k. So this one is just a repetition, guys. Okay, this one is a repetition, that is k. Okay, in place of n, you substitute k. So you're just repeating, just substitute k in place of n. And you're not calculating anything, you're just substituting. It is the statement now that you are going to use later on to prove, just like what we have seen in previous cases. Okay, so this is your matrix, just like that. So in this case, let's say n is equal to k plus 1 now. When n is equivalent to k plus 1, this is where you shall say, I shall prove this and that. Okay, I hope the statement, guys, my statement, I've written it along much. So here, this is what you want to prove now, that when we have got n is equal to k plus 1, then that statement is supposed to be true. All right, so this is what you're going to do. We are going to do, guys. In place of k, remember, we are substituting in place of what? In place of k, we are substituting k plus 1. So let's just take this on a fresh page. All right. So this is going to be 2a 0 1. This was your matrix to the exponent of n, which is now k plus 1. So it's to the exponent of k plus 1, like this, which is equivalent to. All right, so this is what you're going to do. This side you're going to substitute as it is, guys. 2 to the exponent, okay, 2 to the exponent of, in place of n, that is k plus 1, like that. And this one is a 0 here. This one, if you have to substitute, is going to be 2 to the exponent of k plus 1, like this, minus 1 in a bracket. You close the bracket and put a, like that. All right, and this one is what? This one is a 1, like this. So this is what you're going to have. All right, at this stage, now it is going to be us to prove, now to say this side is equal to this side. So like I said, we are going to choose the side that is best for you, and mostly that is the side that is the one that you had from your previous statement, because remember 2 to the exponent of k is there from our previous statement. So we can separate this. Okay, so let's separate. It's going to be, so I'm going to choose to work with the left hand side. All right, that's 20a 1 in this case to the exponent of what? To the exponent of k, which is being multiplied to 2, 0, a1, which is multiplied to the exponent of what? Of 1, of which to the exponent of 1 is just like 1, so you just leave it like that. So this is what you have, and you must prove that from this my answer is going to be like this. So how are you going to prove? Remember previously this statement is there. Where did I write this? Okay, here. So I'm just gonna take this statement here. Remember we had this statement before, so let's take this statement, guys. In place of 2 to the exponent, whatever that we have, I'm going to substitute with this part. All right, so that means we are going to have something like 2 to the exponent of k. Let's just substitute this matrix, guys, as it is. Okay, that's 2 to the exponent of k minus 1 times a 0, 1, like this. That's your matrix. Okay, so this was, you suppose you said when n is equal to k, this must be true, this is equal, so these two, they are equal. So if they are equal, then you can substitute it again, just like saying a is equal to 3, then where there is a, you substitute 3. It's true because your a is 3. So that is the case, guys, but this is to be multiplied to 2, 0, a and 1. This is where you're supposed to multiply it. And if you are to multiply to this, we are back now to our normal multiplication matrices now. So the case is, do you understand row by column? So this is your row by column. Okay, I don't know if it is going to be clear, but let me put this maybe in another ink. Okay, like this. We are going to multiply these two, so it's 2 to the exponent of k times 2 to the exponent of 1, which is just 2, or 2 to the exponent of 1, just leave it like that, plus, because remember you're still in the row, though, this here times s0 here is going to give us s0, which means there's no effect. Okay, so this is 2 to the exponent of k here. All right, now let's move on to this row and this column here. So it's going to be 2 to the exponent of k times a. There is a there, so it's 2 to the exponent of k times a, plus, remember it's row by column, and there's this part which is to be multiplied to 1. Any number times 1 remains as it is, so it's going to be plus 2 to the exponent of k minus 1, like this, times a, which is already there. Okay, so we're done with this row and this column, this row and this column. It's now this row back to this column, so it's 0 and what? 2. That's 0 times 2, which is 2, which is 0, guys, sorry. 1 times a 0 there, which is a 0 also. This row and this column, that's 0 and a, which is a 0 there. 1 times 1, which is a 1. So this is what you have, and from this statement you must work out until your answer is like this, because this is what you have to prove. Okay, is it clear? Let me put it this way. It's now okay, like that. So that is what you have to work until it looks like that. So let's separate, guys, our terms and so forth. Here you're multiplying, actually these are the bases, so you're going to add, because adding to 0 means it's actually nothing here. So if you multiply the base which are the same, you add the exponent, so it's k plus 1, which is 2 to the exponent of k plus 1. All right, what about this part? Okay, let's leave this part from now. Let's just work out this. 0 plus 0 here, that's a 0. Okay, 0 plus 1 here, that's a 1. Okay, now let's work out that part together now. All right, so this is what you're going to have here. What is happening is that this a is going to pose, we want to add, so definitely we can factor out a. As you can see, a is common here, so we can factor out a, because this is a, this is a, so you can factor out a like this. So if I factor out a, because already that's what I'm having, a outside, so if I factor out a here, I'm going to be left with 2 to the exponent of what? Of k. So I'm going to be left with 2 to the exponent of k, plus, because I'm now to this term, so it's plus here. If I factor out this 2 to the exponent of k, I mean this a, I'm going to be left with 2 to the exponent of k minus 1. So this is going to be 2 to the exponent of k minus 1, like this. But guys, as we can see, we haven't proved that. We haven't proved this. So what are you going to do? Okay, let's move on. Let's move on. What is happening here? These are the same bases. It's like you're adding, just like x plus x, you know, that is 2x, because here it's like it's a 1 and here's 1. So you can add 1 plus 1, which is 2. So this statement is going to look like this: 2 to the exponent of k plus 1, 0 here. So this is at 1 plus 1, and it's now 2. So it's 2 times 2 to the exponent of 2k, like this, because you have added 1 plus 1, and that is 2, and 2 to the exponent of k remains as it, just like 1x plus 1x, guys. Okay, then this is minus 1, it remains as it is, times a. Don't expand with a because you want this a to be outside of the bracket, remember. All right, this is what you're going to have here. You're multiplying. If you are to cross check, these are the base which are the same. 2 by 2 to the exponent of k, which is, you're going to add the exponents, which is 2 plus 2 to the exponent of 1 plus k, which 1 plus k is same as what? K plus 1. It's just one and the same thing. So it means I'm going to remain with 2 to the exponent of k plus 1, this one, and this part here is going to give us 2 to the exponent of k plus 1 minus what? Minus 1, like this, into a, and this one is a 0, and this one is a 0, like this. So this is our last stage, and we have to just cross check if it is actually the same thing, and that's actually the same thing that we had, guys. So as you can see, this is actually equivalent to your right hand side. So these are the typical questions that how and what you're supposed to have in this case. So the conclusion, don't forget, guys, your conclusion from those conclusions that I gave you, make sure that you conclude your statement, which is very, very important when you are working with these typical statements, that you prove each and every statement. So I don't know, guys, how you have seen this, but I just want you to work out and try these questions that you have got, try to prove by induction. All right, so this is what you have got there, and these are actually question papers, guys, and this question was having a continuation. Now it was hence now simplify. So guys, like I said, don't hesitate. Your feedback is very, very important, that so that we know if actually we are moving together, or there are some areas that we are still having some challenges that we can work on them on another class. If there is a need for us to actually work on these separately on another class, let me know on the feedback, but just try and do them first. Let us try to work out these questions first and see if we are going to attempt them. Yes, if they can be challenging somehow, then let me know so that we can work on them on separate videos also. So that's what we had, guys, from Mason African Motives, still working on A-level mathematics as we are preparing for ourselves for the exams which are ahead of time. Let us keep on revising, because that's the only thing that we can have for the meantime. And also don't forget to share our videos, guys, to your friends and colleagues, so that they also can benefit from this information. And don't forget also, guys, which is important, to subscribe. Don't forget to do this. All right, that's it till we meet again.